Nikos Evangeliou, he's an expert on fires. He's going to speak in English.
And I apologize for this.
He apologized for that. Next year he'll speak in Norwegian.
Yes.
So, please.
So I will switch a little bit the subject to how the changing climate has affected the fire regime in Europe, basically. This is a very nice, beautiful picture from an unfortunate event that is still ongoing in California. But it's not only there. Several countries the last 10 years have experienced damages from large wildfires. With many casualties, many people were forced to evacuate their dwellings and millions of hectares burned. But the question that is always present in the media is if climate change is the main cause for that, or if we are not environmental conscious enough to face the fires, or if we don't have proper firefighting technology or the right and updated emergency systems. So let's see what happened this summer in our neighborhood in Sweden, that in July, more than 40 fires dotted the country that caused firefighters to scramble and actually thousands of people to evacuate their dwellings. The government asked for international assistance that mainly came from Norway and Italy in the form of airplanes and helicopters. But let's see closely what happens the first 2 weeks of July with temperature from the NASA's Terra satellite. So this shows how the surface temperature compares to a 15-year average, and it shows that in Sweden it was up to 6 degrees higher, a little bit more in Norway, as we saw before. And at the same time, the precipitation was much lower as compared to the previous year, to 2017. So that means that the forests in Sweden were much drier than in the previous years. And this gives a very good excuse to see what happens in a global scale from this nice paper from Nature. So it's a model ensemble, which means that it's a mean from several models. And it shows that the temperature has changed during this period, 1979 to 2013, especially in Arctic and subarctic areas. Actually, this increase is similar to what the IPCC has predicted, around 0.25 degrees Celsius. The relative humidity has also gone down, especially in the western part of USA, but in other areas such as Alaska. The rain-free days also increased, again, in areas that traditionally they give large wildfires, such as Northern America. And the wind speed has stayed constant, more or less. If we see it annually, we see that the fire weather season length has increased, actually after 2000. The same for the area affected from this increase in the fire weather length. And also the rain-free days with a smaller trend, actually. And here it shows this change in fire weather fire season spatially. And again, it shows that areas like western USA or the Iberian Peninsula that gave this summer lots of fires were affected. Despite all this, the global burned area goes down, as this nice science paper shows. Actually, we knew this from many years ago, but we didn't know the reason. And it seems that the reason is that the agricultural expansion and its intensification basically in savannas and grasslands. So the paper states explicitly that when it's about large wildfires and closed canopy forests, this global burned area goes up and not down. This gives a very good pass to see what happens in the forests of Europe. And here I show the standardized precipitation evapotranspiration index, which is basically an index of drought of the forests. So when it's positive, it means that the forests are wet. When it goes towards negative values, it seems that it shows that we're going to more dry forests. And we see here that the last 20 to 30 years, this trend has been going down, and since 2002, we have only negative values more or less throughout the year, which means that forests in Europe have become very dry. And here it shows that the anomaly of the forest fires in Europe as a function of this drought index, which is increased for drier forests, for example. This picture shows on the left the burned area as a function of tree cover, which basically confirms what this science paper that I showed before says, that the burned area is very high for low and intermediate level of tree cover, whereas when we go towards large forests with a large level of tree cover, we have less burnt area. But this 95th percentile is high, so it seems that they're kind of important. And if we multiply this burned area by the tree cover, we get the forest fire risk, which is nothing more than the risk of a forest fire to spread. And we see that the largest risk is for Eastern Europe, where mainly there are many forests there, especially close to the Chernobyl area in Belarus. Also in Portugal, that after this publication basically gave lots of fires, and again in southern Spain, Greece, whereas we note that there is some risk in Sweden mainly, but the risk is not so high as we would expect after this summer, for example. So why are we so interested? I'm not going to talk about the socioeconomical consequences of the large wildfires. I will rather focus on the environmental ones. So these wildfires burn in temperatures of more than 1,000 Celsius degrees, with flames that can reach up to 50 meters altitude, which means that whatever is emitted there can be transferred in tropospheric altitudes or even in the lower stratosphere. To form these pyrocumulus clouds that look like something like this, for example, and they can change the weather patterns of regions. So once they're emitted at such high altitudes, they're subject to long-range transport, so they can be transferred far from the source. Like last year, we got several complaints from areas in the western part of Norway they complained about the smoke of smell, and then we were asked to see where the smoke was coming, and we found out that it was coming from the large fires in Portugal and the plume that arrived in Norway at the time that we got the complaints. Here is a viral picture from the Zeppelin mountain in Svalbard during a smoke event and a clear sky. This is to show that since all these substances, such as aerosols, are subject to long-range transport, it can be transferred to the Arctic, deposit on snow, and act as light-absorbing impurities with already well-known effects on these surfaces. And in a few years back, we estimated that from the black carbon specifically, that deposits over the Arctic, about 40% is coming from anthropogenic sources and 60% from biomass burning, which is quite high. So the last example that I would like to show you here is from the last year's fires in Greenland. Here I've plotted the number of fires per year from the MODIS tool, the MODIS active fires, and we see that in 2017, the fires detected by the satellite, by the instrument, were 6 times higher than in any other year since the time that the tool was founded. The event was captured very well by some pilots that flew nearby and also by satellites, such as this Sentinel. And using these satellite products, we were able to calculate the burned area and then model the whole event. Actually, the transport and the position of black carbon that was emitted from these fires. It wasn't a long event, and there were about a few kilotons of black carbon emitted. But we found that about 30% of the emissions deposited in Greenland's ice sheet. And although this doesn't have a large impact on the albedo of the Greenland ice, we think that it's a very important finding if we think like in a per unit basis. So if we think that 30% of the emissions that was deposited in Greenland. Taking into account also that the fuel in Greenland, there is no vegetation basically, apart from permafrost, everything is permafrost. So there shouldn't be any fuel. And the fact that there were fires here, it means that there were pit fires, it's only pit there. And pit is the earliest formation of coal, which means that it contains enormous amounts of carbon. So, and then I found this quite old paper that shows that the thawing potential, so the potential of permafrost to melt in these areas is huge, which means that if we continue to act like in the climate and the temperature goes up and precipitation still continues to go down, we could expect more fires in the area, which is not good at all. Then I decided to do some future predictions about the burned area and the carbon litter accumulation over the forests in Europe. And for this reason, I took one of the IPCC scenarios. Not the most extreme one, not the least extreme ones, but I took this intermediate, this A1B, this green line. And then I used the LPJ Spitfire model, which is a process-based fire model. And it takes many physicochemical parameters, such as temperature, soil moisture, and examines actually the relationships between carbon stock and storage with burned area. So here is the litter accumulation until 2100. And we see that the litter accumulation becomes more important to the northern latitudes, where many forests exist, so in boreal forests, basically. And the burned area over Europe increases. Also, the variability increases, of course. So this increase, of course, might be smoother in the future if the temperature and the precipitation pattern are kept like this, like in the A1B scenario. But of course, it could be smoother because the technology evolves and we will have more emergency systems and better firefighting infrastructure. So instead of conclusions, I would like to say that all these wildfires and effects from the changing climate to forests is a closed cycle. So with increasing temperature and precipitation going down, we increase the duration of drought and the intensity of drought. Then the forests die. We have more available fuel that is actually vulnerable to fires. And if fires continue to burn, we have more aerosols and gases to the atmosphere that puts a lot of stress, more stress actually, to the globe and to the climate. Thanks a lot.